You give me instructions, right? Well, I suppose you did. Curioso. Para ver se tá para ver se que eu tique.
Kom je erbij even?
Oh, no. No, het is toch goed gepaard, toch?
So, at exactly 10 o'clock, we come into the door. I'll ask the people to stay left. Then the defense starts. The chairman asks you to take a position behind the lectern. Both of you please follow with your pieces. Maybe you can put it on the 10 minutes later also,
But
we will be back.
I can keep talking until she hits the floor.
Yeah. 10 minutes later also we will be back with the diploma.
Right.
Then we will come to that door. I'll ask again the people to stand up. Then the chairman asks you to take a position in front of him, so second chair, with both of you behind you like a V. Let's practice, just to be sure. So no, second chair.
My turn. Second chair.
Second chair, yes. Then you get your diploma, probably from your promoter sitting over there.
Right.
And then I will say you may all sit down, except the three of you are staying here until the end, please.
Right.
So until the chairman says you may not have to sit in the room again. Clear until now?
Yep.
Then we will all leave. I'll ask you to follow us. Is someone going to make pictures?
Yes. Where's the Miché? Oh, he's in the toilet.
Oh, and then we're going to make some pictures at the stairs.
Yeah.
Okay. First alone with the committee members and later on with your family if you want.
Okay. Yeah.
Is there a reception in this building?
Yes.
Then we will all go to the reception.
Okay.
Dus after the picture taken at the stairs, I'll ask you to pick up his belongings. In the Senaatszaal behind this room. And also check if no one forgets anything from the audience, please.
All right.
And clear?
Yep.
Take care of the water. It's better to leave it up there, but if you
Walk it to there to
so, of course, but you can also leave it there, but please be careful, because when it falls down, you have a problem.
Yeah,
Also,
there's no point that's gonna get wet.
If it falls down, your defense is done.
yes, but we have to do it over again. No jokes. If it stops, we have to also with fire.
Okay, that's alright. Just to keep your mouth on. That's alright.
Alright.
Or she can stay to the
Wel. Oi? Oi, Ferreira. Oi, mamãe. Yeah. Keep it. Turn off. Okay. Good morning, everyone. Thanks for coming and Happy New Year. So in the next 15 minutes, I'm going to give you a brief introduction about my PhD research. I'll be switching between Portuguese and English, just to make sure that everybody's going to follow up. And my research is about the effects of a stratified tidal flow on the morphodynamics. I'm going through with you in the next 15 minutes. I'm going to tell you what did I look at to understand that, why is it important, the research approach, and the main finds, and then a brief summary, right? And to start, so everything started in Rio when I applied for this position, and then I moved all the way to Delft. That was in 2013. So let's start understanding the title. Desculpa, esqueci do português. O título é sobre os efeitos da corrente de maré estratificada na morfodinâmica. Eu vou explicar agora. So, what I mean by stratified flow is like when you have two flows with different densities, like water and oil. This also happens in the ocean. Quando você tem dois fluidos com densidades diferentes, que nem água e óleo, isso também acontece no oceano. So by morphodynamics, I mean that, everything that moves on the bottom, so that the sand is moving back and forth due to the influence of the overlying fluid. Isso daqui é morfodinâmica. A morfodinâmica é o movimento do fundo do mar, por causa da corrente, do fluido que está em cima. Right. And I'm especially interested in the process that happened in deeper water. So that's why I called here inner shelf, but not the whole Dutch inner shelf. So here's the Dutch coast. I'm interested in only this bit here that's between 8 meters and 20 meters depth. And why is it important? So the first thing, most of you guys know, at least the Dutch ones, that the Dutch coastal policy says that the volume of sand should be maintained from the dune foot plus 3 meters to minus 20 meters depth. Então, existe uma política aqui na Holanda para manter o volume de areia da costa inteira, que vai da duna até 20 metros de profundidade. Second, so most of the studies here about sediment transport, they talk about they are more in the shallow part of the shelf where the waves are dominant, and then I'm in the deeper part where the tides are more dominant or They have equal contribution of tides, wind-induced flow, and other processes. And also, it's more likely to see mega nourishments like the sand engine being implemented in all over the world. And those big nourishments, they can extend beyond the depth of 10 meters. Então aqui tem uns engordamentos de praias mais modernos, que eles é uma quantidade imensa de areia que vai até 10 metros de profundidade. Então eu estou interessado na parte mais profunda do que o que acontece na parte mais profunda da costa holandesa, onde a onda não é tão importante assim. Right. And my thesis is structured in three main parts. That is hydrodynamics, bed form behavior, and sediment transport. I'm going through all of them with you now. And I think 95% of my research was based on data, field measurements, and the hydrodynamic part, we measured the currents in this section here. So if you look at the bigger picture, here's the Dutch coast, and we are 10 kilometers away from the Rotterdam waterways, and just seaward of the sand engines, there's a mega nourishment here. Então, minha área de estudo é perto do Rotterdam, do Rio Reno, e perto desse mega nourishment, desse mega engordamento de praia aqui. Right. So what we did here first was to measure the currents with a boat, looping around 2 transects for an entire tidal cycle, and also, since I'm interested also in stratification, I'm going to explain later, we also had a jet ski collecting CTD profiles while you were measuring. We also had a frame that was deployed at -12 meters depth, and the frame was measuring near bed velocities in high resolution, ripples. There is a 3D scanner to measure the ripple dynamics, and also a device that measures the concentration profile called ABS. So this is the sand engine, I'm explaining again. So esse daqui this is the sand engine after its completion in 2011, and then the amount of sand is equivalent of 1 million dump trucks. A quantidade de areia é equivalente a 1 milhão de caminhões de areia botaram lá no início, depois que construiu. But by the time of our measurements, the sand engine looked like this. Was more or less 300 meters in the cross shore and more or less 5 kilometers in the long shore. So one of the things that are very important in my research is the effects of stratification, as I told you before. And if you look at these satellite images, we see that the Rive River plume extends all the Dutch coast. And this red arrow here is where the sand engine is. Oh. And just to have an idea how the hydrodynamics changed how stratification changed the hydrodynamics, I'm going to show you a very nice animation by Gerben de Boer. So what you see on your left is the situation without stratification, and here on your right is the situation with stratification. So this is the profile of the tidal current. So you see that here, the tidal excursion is really back and forth, right? But when it's stratified, we see, oh, sorry. When it's stratified, we see that the tidal excursion is more circular, and this is very important. And we also do that, and I'm especially interested in what happens near the bottom, where we also see these change of the tidal flow due to stratification. Então, a corrente de Meirelles muda quando está estratificado, quando tem a presença da pluma do rio. So, first part, hydrodynamics. The main question that I wanted to answer here was like, what's the contribution of stratification? Because we have many other processes there, and I want to pinpoint how important stratification is. And the second question is how this change in the hydrodynamics due to stratification is translated onto bed stresses. Because in the end, ultimately, I'm interested in sediment transport and bed form dynamics. So answer the first questions, don't get scared, but I had to pinpoint all the terms of the momentum balance. It seems very difficult, but, well, by the time it was, but now it's not anymore. So I look at local acceleration, the vective terms. Centrifugal acceleration was important because of the same engines. It can induce, the curvature of the same engine can induce secondary flows, like cross-shore exchange flows. Coriolis accelerations, and here the force, like pressure forces, and also frictional forces. All right? But all you need to know that we measured that, we calculated that. What you see here, it's time, like one tidal cycle. Here is the forces and accelerations, and here's the velocities. The curve here is the dissipate velocities on the surface, and here on the bottom. And I just want to draw your attention for the main results that if you look at the baroclinic pressure gradient that's due to stratification, you see this cross-shore tidal flow is really dictated by stratification. You see the changes in the black bar here sort of dictates the changes in the velocities. So, right, we answered this, and then later we wanted to know the effects of that on the bed, like in the bed shear stresses. So what you're looking at here, what I did, I have a time series, right? And I got chunks of 12 hours of this time series, like one M2 tidal cycle. I got the chunks, I stacked them together and averaged them out. So it's what you see here, like a M2 averaged chunks of the series. So I have two spring tides, and the first thing that I want to tell you is that this is the tide bed shear stress, the red line. The residual is this purple here, and the orange is wave bed shear stress. And you see that the tide bed shear stress is way higher than the other ones. And also, if you compare that to the stratification that's in this X here, is the red line. So you see that's sort of, when the stratification increases, we see that the bed shear stress is somehow prolonged. So my interpretation of that stratification sort of prolongs the time that the bed shear stress is acting on the bed. So part 2, morphodynamics. So since I'm interested in stratification, I had to look at the series and pick situations where the water column was stratified and situations where the water column was mixed. So the two questions that I want to answer was like, how do ripples behave under stratified and non-stratified conditions? And then what's the impact of stratification on the ripple migration, on the bed form dynamics? Agora eu estou olhando para o fundo. Primeiro eu olhei para a hidrodinâmica, agora eu vou ver como essa estratificação afeta o fundo. So, I did the same analysis that I explained before. I got chunks of Me2 12 hours, averaged them together, right? And what you see in blue, it's stratified, and then what you see in red, it's well mixed, how I define here. So the first panel here, what you see are the shear velocities. So they look pretty similar during high water, and then during low water, you see that spring one that's stratified is slightly higher, and the dashed lines here are the critical velocity for sediment suspension. So we can understand that everything that's above this line here is going to be in suspension, and you see sort of more suspension here when it's stratified. But they have similar magnitudes, right? And here's just to show that here's stratification. All I want to show is that you have much more. The water column was strongly stratified here in blue, and in red wasn't, although you see some peaks here. And now it's important, like the effect of that on the ripples. So you see here the ripple. Here's the ripple height. So in 12 hours, the ripple when in the well-mixed conditions, they're much higher than the ripples during stratified conditions. And these we also see in the ripple asymmetries. So during stratification, the ripples are more symmetrical. That means that they're less developed, while they are more asymmetrical during the well-mixed period. And by the end, here's the migration rates. So the migration rates are much higher as well when it's non-stratified. So our interpretation for that is like, why you see this difference if the magnitudes are similar, right? So we understand that first, here I'm just showing the growth rate of the ripples. So when it's stratified, the ripples grow like 1.5 times faster than when it's stratified. Here in blue, here's just time and the normalized height. So see the growth rate of the ripples. And here is an interesting thing. So since they have the similar magnitudes, so why would explain this difference in ripples? So our understands that due to stratification, the circular path of the tide doesn't allow the ripples to develop. And we could show that here in this diagram here, where you have, during spring tides, you have basically one dominant direction during ebb tide stage, because the ripples grow during ebb. During flood, it's basically the bed erodes. So it's basically one dominant direction, while when it's stratified, you see that the durations are smaller. So we calculate that this is more or less 58% longer in one direction than this. That's the dominant direction during stratified period. Right. So to see here, I just want to show the circular motion of the tide and the non-linearities. What you see here, I just got the velocities and I integrated them, so I have now displacement. And again, in blue, you see the stratified condition. In red, the non-stratified, and the dots here are 6 hours apart from each other. So you see, like the dots, they're far away from each other during stratification, and when it's non-stratified, they're basically here. That means that the stratified flow is more, they're more asymmetric, and because of that, you see the drift of the tidal flow, it's longer. And these reflect on the ripples. I won't tell the details of this figure, and also I didn't have the help of my kids to do this. This is really like data. But I just wanted you to see the net migration. So the net migration during stratified period sort of follows during the behavior of the stratified flow, but then the net during the non-stratified conditions is much smaller. So again, this sort of reinforces our hypothesis that the circular motion of the stratified flow is responsible for these changes we see in the bed. And now we want to see how this affects the sediment transport. That's the final part. So it just first insights on the impact of stratified tidal flow on the bed load and suspended load transport. So here's just a diagram showing the bed load here in brown, and here's when it's stratified and when it's well mixed. So the bed load, when it's stratified, is onshore directed and higher than the bed load when it is well mixed. And the suspended load is going to the north, right? And when it's stratified, it's also onshore directed, and when well mixed, it's more offshore. And the suspended load when it's stratified is a little bit smaller, and this might be because we see some resuspension during ebb tide. So we have a lot of resuspension during flood, but also resuspension during ebb, and because of that, we see a slightly smaller suspended load when it's stratified. So just to summarize, so this is the diagram in front of the same danger. So suspended load, bed load along shore, and here cross shore, and that's the situation when it's well mixed. So have offshore directed, and here is greater than here. And just to recap quickly, so we see that how the stratification influenced the velocities. how, because of that, these velocities are translated into frictional force and impacts the ripples. And also, you see that it's more about changing direction than changing the strength of the flow. And then you see this pattern in the bed loading and suspended load transport. So the final conclusion is like the stratified tidal flow modifies the geometry and dynamics of the ripples, which ultimately affects the bed load and suspended load sediment transport. And yeah, let's party tonight. Thank you. Right on time.
Misschien ook... Oh ja. Oh, misschien kun je nog een beetje opruimen. Wilt u opstaan? Gaat u zitten.
Ik open de zitting van de commissie ter beoordeling van het proefschrift en de stellingen van Saulo Meirelles Nunes da Rocha, Master of Science in Coastal Engineering from Brazil. De verdediging zal in het Engels worden gevoerd. I request the promovendus, together with his paragonims, to take their position behind the lectern. The Board for Doctorates of the TU Delft has installed a committee to evaluate the dissertation and propositions. The committee will have a debate with the candidate in public, and it is an honor for me to present the members for this committee, to whom I extend a hearty welcome. First of all, we have Professor Valkes. He is from the University Politecnica de Catalunya, from the physics department. Welcome. Next to him, we have Professor Roelvink. He is from IHE, the Delft and also from the Delft University of Technology. Also, welcome. All the other members are from the Delft University of Technology, from the Faculty of Civil Engineering and Geosciences. First, Dr. De Schipper. Then, next to him, Professor Arninghoff. On this side of the table, we have three promotoren. So first, Professor Pietrzak, Professor Reniers, and then Professor Steven. Thank you all for taking part in this academic ceremony. My name is Kees Fuik. I'm Professor of Applied Mathematics, and it's a pleasure for me to chair this session on behalf of the Rector Magnificus. I would now like to start the opposition and give the words to the first opponent, Professor Valkes. The floor is yours.
Thank you very much, meneer de Rector. Waarde promovenda, I am very happy to be here and very honored to be in this committee. I enjoyed reading this thesis. I must admit it's a bit far from my own expertise because I am more in shallow water. But it's a good opportunity to learn about these more deeper processes and, well, tide and so on. Okay, I have a couple of questions. First of all, about one of your conclusions, the research question 1.3. You say that the shoreward extent of the cross-shore tidal flow, with, well, stratified, in this case, can be up to 6 meters depth. Okay? So then my question is that what could be the influence of these cross-shore flows on the cross-shore beach profile, okay, and on the depth of closure for in the near shore, and also you know that in the Dutch coast, for instance, the breaker bars, they migrate systematically towards the sea, no? And at some point they vanish, right? Maybe this cross-shore flow could be related to this vanishing of these bars at these water depths. This would be my question, no? How this can affect your research, could affect my own research in intermediate water depths, right?
Right.
Waarde promovendus, is the question clear?
Yeah, it's clear.
Please defend your thesis.
Hogelarde opponent, thanks for your question. Yeah, as you could see, this cross-shore flow extends up to 6 meters depth, maybe more. I haven't looked at the influence on the cross-shore profile, but thinking about that right now, we have other processes going on there, for example, undertow and the influence of long waves. So I wouldn't be able to tell which one is important for comparing with the cross-shore flow, how the cross-shore flow would influence those bars. What we know is that it's definitely important for the sediment transport, especially fines, this combination between waves and the cross-shore exchange flow, because we have one of the researchers from our group. He could see that the waves are in charge of suspending fines and also coarse sand. And then this can, especially the fines, with the arrival of the front from the Rhine River, pass by at least when the front arrives, we see that this cross-shore exchange flow brings all the fines to the offshore part all the way to 12 meters depth, right? So this possibly has an effect on the coarse part as well that would influence the bar. But yeah, so I believe that there's possibly an influence, but I would hear, at least my best guess, that we could neglect that, I guess. And regarding the depth of closure, well, that depends on the time scale. If you look at longer time scales, I do think that there's an influence. So we should give more attention to this cross-shore exchange flow in the longer time scale. But in a shorter time scale, I think waves would be in charge to explain this, the depth of closure. And, and that would ultimately affect the beach profile. But yeah, so the bars, I think, would be more influenced by the waves, although the cross-shore exchange flow could have some influence. But I couldn't tell you how much would the influence.
Yeah. Because, for example, which is the magnitude of this cross-shore flow, the tidal cross-shore flow at this water depth of 6 meters or so?
Well,
approximately?
Yeah, we're talking about maybe 20 to 30 centimeters per second.
Mm-hmm.
Yeah.
Okay, thank you.
Yeah.
Then I have, Meneer Director, I have a question on Proposition 5.
Waarde promovendus, can you or one of your partners read Proposition number 5?
Yeah, please, Max.
Planning for future large nourishment projects such as the sand engine should consider the proximity of freshwater inflows to the northern side.
Thank you.
Okay. Yes, I wonder, and I'm very interested about what would be the influence on the global morphodynamics of the sun motor, taking into account these tidal currents, both the longshore and also the cross-shore you are studying in your thesis.
Right.
Because you talk that it can influence, but have you seen in which way, or have you investigated a little bit, or you know which could be the effects? I am very interested in this.
Yeah. So, Roger, the opponent, thanks for your question. Yeah, so one of the things that I looked at more specifically was the influence of the curvature of the sand engine, right? So, first off, it's a kind of nourishment that sticks out all the way to the 10 meters depth. If you look at the original coastline, and then after the construction is 1 kilometer, right, in the cross shore. So one thing that I looked at was the effects of the curvature, and well, and then it comes again to the bar things, right? If you go to the shallow part. But in the deeper part, we found that the curvature or the curvature-induced cross-shore flow was important probably in the first 3 years of the nourishment. And then as was eroding, as was like spreading, then the effects, in this case, the effects of the stratification in the cross-shore was more important. So yeah, I would your question was first about the nourishment. So close to the river mouth, I think is important because normally those river mouths, they are engineered, right? So you have like the obstruction of the longshore transport normally. So that's the first thing. And the second thing is the stratified flow itself, how it changes the hydrodynamics, and how would influence the dynamics of the nourishment itself. So about the cross-shore transport, I believe that would be, in this case, pretty much driven by the barotropic tide, so stratification, and the alongshore transport. Then I think that the baroclinic in the cross-shore and in the alongshore, I think the barotropic tide would do the job of both. I mean, wouldn't differentiate that much.
Yeah, thank you. But in your opinion, what would be this cross-shore transport? Would maybe help to decay or to build the nourishment? In which way? Is it?
Right.
Maybe it's a difficult question. But you have an opinion on this?
They also would depend on the alongshore gradients, right? Because the profile is also shaped by the alongshore gradients in sediment transport. So you also should look at the alongshore sediment transport. But maybe if you look at the example of rivers, where they have the banks due to the same kind of circulation. So maybe then again, maybe you could have those, it would help to keep the profile steeper. But since you have also a longshore, a very strong alongshore gradient, then there would be not significant because of the alongshore component. Because we also see very strong alongshore gradients there, and there are people looking at that in the barotropic tide in the longshore.
Okay.
Was that clear?
Yeah. Thank you very much.
Yeah.
Okay. Thank you for the opposition. Then we go to the next opponent, and I give the floor to Professor Roelvink.
Yeah, by the promovendus, I was also read your thesis with a lot of interest and interesting data and analysis. But I have some issue with your proposition number 2.
Well, promovendus, can you please read proposition number 2?
Boss.
Waves play a secondary role in the sediment dynamics of the Dutch inner shelf.
Thank you.
Okay, and so I have some questions related to this proposition, and maybe we could have a look at your figure 5.1 on page 56 first. And then, I don't know if people can see this, but I see, for instance, I think I see quite some effect on the ripple height of the waves. So there are several events where the waves are not very high, but maybe above 1.25 meters, and every time I see the ripple height more or less double. Could you explain this, how this is not important?
Yeah, it's clear. Hooggeleerde opponent, thanks for your question. Just to clarify, I don't say that it's not important, but I say there's secondary importance. So it's still important. However, if you look at the two things, the tides, if you look at the stresses and compare the stress of tides, waves, and and residual, for example, due to winds, you see that the stress due to tides, it's just a periodic thing. Every 12 hours we see that. And wave, in this case, is more episodic. If you compare the magnitudes isolated, yeah, I agree with you that waves are, the primary importance. But if you look at in a longer time scale, and you see we do have, for example, in this 4-week series, you have 2-3 wave events, which, well, we see these effects on the bed, right? But however, we see especially in spring tides, we see that the ripples really follow this same diurnal behavior, the ripple height, which means that the tides are periodically changing the bed, while waves is more episodic. So, yeah, because of that, I think waves in the inner shelf, they have a secondary flow, a secondary role, while tides, since they are just there, all we depend on is the movement of Earth, Moon, and Sun. In summary. So, and it's all the time like moving the bed, and that's the idea behind my proposition. But if you compare magnitudes isolated, yes, I do agree that waves they have more power, especially because the boundary layer is is smaller, then you have more stresses.
Yeah, and in terms of the types of ripples, huh? There's another figure on page 50 that tells us what kind of type the ripples can be, huh? And I see that every time, of course, when the waves are a bit higher, then the same instances you see at least a mixed type of ripples, huh?
Yeah.
But how do you know that those are not the important times? Huh? Because, okay, the ripples, the bed load goes back and forth every tide, but does that lead to an important net transport?
Right. Yeah. Jorge Lerda, opponent, thanks for your question. I haven't quantified the net transport by waves, the bed load. Although, yeah, as I said, I believe when we have a wave event, they are really high. But to answer that, I think I should, I should first compute the bed load by waves and have more, maybe not yearly, annual scale, and then see how waves and tides compete in terms of transport. I do get your point about having the waves as an important process there, but it's still I see as a more episodic event in the inner shelf. And if you look at, we do need to have waves maybe higher than 1 meter, 1.5 meter to see those big things, those big jumps in the ripple height. And again, the tides are just there every 12 hours going back and forth. So possibly in the cross shore, if you look at the cross shore bed load, the net, maybe the waves are more important, but I haven't looked at that. So.
And how do you think this 30 days you are already referring? You should look at a whole year, but these. I mean, is 2 meter wave height at 12 meter depth, is that an extreme wave height, or is this something that is rather common in winter?
Well, we do have a lot of storms here in the winter, right? Mm-hmm. And but we also have measurements in the winter, not this one, it's not shown here. And I think we also was about 4 weeks measurements, so we had one big storm, and this also was one big storm. So then then the transport, the bed load transport on the inner shelf would be more episodic driven. Only we should need these wave events to see big changes. And I think that if you have like one storm, 2 big storms per season, so to say, then I still think, although I haven't quantified them, but I still think that the bed load by tides would have a bigger impact.
Okay, well, if I may ask one more question about that bed load transport then. If we look at figure 5.5 on page 64, very interesting results, I think. So what we see is that the migration rate is bigger during ebb than during flood flow, huh? And that indicates that you also have a bigger transport, and so your net transport ends up to the south, huh?
Yeah.
Bed load.
No,
Why?
no.
Why is this happening? Because the flow velocity seemed to be more or less the same in both directions. So why is the migration rate bigger during ebb flow?
Through ebb, right. So, Jorge, the opponent, thanks for your question. This is because during the flood stage of the tide, have more suspension, so the bed's eroding. If you look at, so here, so this high water, okay? So if you look at the ripple height, it decreases quickly near the peak of high water. So the bed's eroding. And then if you look at here, the stresses. So this is the shear velocities, and the red line is the critical velocity for initiation of a suspended sediment. So you see that most of the suspended transport happens during flood. And then during ebb you have smaller velocities, and then the ripples are able to grow. And then as we have less erosion of the bed due to stresses, then they migrated following the ebb flow and not the... So we have a lot of sort of sorting. So we have a suspended sediment going to the north and the bed load transport going to the south.
Thank you very much.
Thank you for the opposition. Then we go to the next opponent and I give the floor to Dr. De Schipper.
Thank you, meneer de rector. Waarde promovendus, congratulations on a fine thesis. I have read it with much interest. I learned a lot. It's not an easy task to obtain data, analyze and draw conclusions from data on the shore face. And I think you did very well. Nevertheless, I have a few questions. And actually, I would like to follow up on the question of my neighbor on this figure here. As you started to discuss, panel D shows in black the ripple height variations over a tide if you average multiple tides, right?
Right.
Can you once again explain what happens to these ripples as you go through a tide? Why do they decrease and why do they increase again?
Right. The opponent, thanks for a nice question. So, as I was explaining, during during flood here, high water, just recalling that the high water here coincides with a peak of velocities, tidal velocities, right? Because of the Kelvin wave behavior of the tide. So we have a lot of stress on the bed. So this is seen here. So I want to show this here. So this gray region here shows resuspension. So because of that, the bed erodes, and so is so are the ripples. And the ripples, let's say, the ripples don't have the chance to develop and migrate, although we see some migration, but most dominant process during flood stage of the tide is suspension, have a lot of stress due to the flood currents being much stronger than the ebb currents. But then, have slack water, and the bed is sort of washed out. And then when the ebb currents start to develop, so you see that the bed growing again. So the ripples are developing. However, you see that the resuspension during ebb is much smaller, so you don't have a lot of resuspension. The sediment's not being picked up from the bed. So the ripples can grow and also follow the flow. By this, I mean migrate.
But if I would have to guessed beforehand. I would think during more energetic conditions, ripples are larger in size, in amplitude, as the more energetic conditions usually create bigger ripples. So why isn't that here the case?
There's a threshold for that. So the ripples grow at some point, and then they reach equilibrium. This is also seen by you see that at some point the ripple height just stays. I'm not saying that they are in equilibrium here, but maybe near equilibrium. So they don't grow. If you look at a ripple growth curve, it's sort of exponential. They grow very quickly, as you see here, and then they sort of stabilize. And maybe there's something to do also with the scale of the bed forms. Maybe for dunes, that would be true, like stronger flow, then you would form ripples, but dunes or large-scale bed forms. For the ripples, what happens is that they are just washed out. So there's a threshold. I think that's the main point that you want to know. So they're going to grow at some point, and then once the sediment's being picked up, they cannot grow anymore because you're removing the sediment from the bed.
But yeah, I think that's also what you mentioned in part of the text, that you say there's washed out ripples.
Yeah.
But then I wondered, if you have washed out ripples and you compute the bed load transport of that, can you use sort of a geometrical analysis where you use the front side of the ripple and the ripple migration, or is there actually more set bed load transport over the ripple itself?
Well, one thing is important. The types of bed load we can discuss here. So the bed load I'm talking about in my thesis is the bed load due to migrating ripples. So I'm assuming there's no, the grains are not jumping around, but just due to the ripple, we do have some bed load, but that's the assumption behind of the bed load I'm looking at. So maybe you're right. When they are washed out, we probably have some other kinds of bed loads, but not due the migrating ripples, because the way I calculated, I used the measurements from the 3D scanner, right? And then I just did the correlation between the images, and then found the time lag between the images, and then from that I got the migration rates. So that's the assumption behind of the bed load I'm talking about. It's nice also to make this clear here. That's about the bed load due to migrating ripples. So if they are not migrating, in my assumption, so there's no bed load.
So if your formulation might underestimate the bed load transport because there's also transport going over the ripples, how would that affect sort of the balance between onshore and offshore? Would it affect that balance?
Onshore, offshore, I don't think so. Maybe in the longshore, yes. In the cross-shore, no. Why? Because of when the cross-shore flow is mostly dictated by the stratification, right? And then, if you remember, when it's not stratified, you have sort of rectilinear tidal flow going north and south, so to say, parallel to the coast, right? So and slightly offshore, but it's much smaller than the stratified cross-shore flow. So because of stratification, then I do believe that it would still going onshore, regardless of the bed geometry. But the alongshore, yes, maybe you might be right in the alongshore that possibly this net would change. Then maybe gonna have more or less southward transport, or maybe even to the north, the bed load. But if you assume that it's due to migrating ripples, then yes, to the south.
Meneer de rector, am I allowed to ask one more question?
Sure.
Then I would like to discuss proposition number 10.
Father Promovendus, can you please read proposition number 10?
Natural selection explains why the world's tallest nation is found in low-lying lands.
Waarde Promovendus, I'm intrigued by this proposition. And I brought some statistics of length, of average height of male. So I selected a few countries. might be familiar with. And one of the things that's interesting is that from sort of 1950s onward, so people born in the year 1950s, these people are taller than the Swedes. And so my question to you is, how does this relate to sort of natural selection, or how do you see that low-lying country in this data?
The related opponent, thanks for the question. I would like to start off with that it's definitely natural selection in course. So if you look at that, for example, United States used to be the tallest nation a few decades ago, right? If you look at there. And then first, by natural selection, it means that in this case, like the most successful group in reproduction are the taller group, right? That's why you see this difference. Is getting, you guys are getting taller, right? So it means that the taller group has more success in reproduction, right? And there are many things that could explain that. For example, healthcare in the Netherlands, or maybe taller guys, they are more attractive for the females. Yeah, but this is really is the case. That's how natural selection works. But in the case of the Netherlands, you would think, because you could, by elimination, say, well, but in the United States they were also tall and wealth and everything, had good health care. So they would explain the Dutch case. Or maybe it would be comparable, because now they are not tall anymore. And if you look at this peak here, it's around when the flood of 1958 or so happened, right? So now when it comes, so if you are a woman and you lost your grandpa during the flood, he just drowned because he was short and stuff. So by instinct, when you're gonna choose your husband, then you're gonna choose the taller one. So because he's going to survive some eventual flooding in the Netherlands, and don't want to see that anymore, right? If you already lost your beloved ones in the past, so you choose the taller one, and there's a natural selection course. Did I make my point?
I think it's an interesting theory.
We should write a paper about it, maybe.
Meneer de Rector, I think I have.
You are satisfied with these answers. Thank you. We go to the next opponent and I give the floor to Professor Arninko.
Thank you, meneer de Rector. Waarde promovendus, as a product of this natural selection, I highly appreciate the answer that you gave to my previous opponent, although it comes with disadvantages as well. Congratulations with the completion of an interesting and rewarding study, I have to say. Over the years, there have been several attempts to study the dynamics of the River Rhine freshwater outflow, and every time it has proven to be a challenge to fully grasp the detailed physical processes that play a role. And I highly appreciate your contribution to these studies, particularly that you relate your investigations into the field of morphodynamics and morphological processes. Now, I have two issues that I'd like to discuss with you. The first one relates to the stratification and its effect on bed shear stresses. And the second one to the upscaling of your findings to the design of large-scale nourishments. Now, let me start with the first. And the first I'd like to do on the basis of figure 3.4. That made me thinking. What you present in figure 3.4 are the outcomes of your data analysis of your 2013 experiments, which was which covered a 20-day measurement period. And in this figure, you present the individual contributions to bed shear stress of the tide, the waves, and the residual component, averaged over the 2 spring periods that were covered by your experiment. Now, the first thing that made me thinking was, if you look at the wave-induced contribution to bed shear stress, and I do think we need a figure by now.
Bas?
There you go. That is the little yellow line in the lower figure. It peaks twice, both at high tide and at low tide.
Yeah.
What is the physical explanation for that?
Jorge Larda, opponent. Thanks for your question. And that's actually a very interesting thing that we've discussed before in our group about this. We see this tidal signal on the wave, right? And then that comes from the wave orbital velocities. If you calculate the wave orbital velocities, you're going to see that. I don't have an answer for that, and I hope someone is looking into that because it's quite interesting. One thing that we think that could be the reason to see this tidal signal in the wave is due to the shift of the wave spectra during high tide and low tide. So low tide is very low frequency, right, in the spectra. And then we have the wave spectra in the higher band of the velocity spectra. And then when we have, I don't really recall it very well, but when you have low or high tide, you have this shift. And then the frequencies kind of overlap. And since the way we, at least in this work, calculate the orbital velocity was based on the spectral analysis, so maybe some tidal signal escaped to the wave signal or so. And then we see this tidal signal on the wave batch stress, on the wave orbital velocities. But I know other people that also did that, and the results are always the same. We see this tidal signal on the wave orbital velocities. But the physical explanation specifically, I couldn't elaborate more on that, but one of the things we at least speculated was about the shift of the spectra during high and low tide.
Because normally you would probably expect a larger water depth, smaller influence, and vice versa, right?
Yeah, yeah.
So this effect dominates.
Yeah.
All right.
But still not proved, but it's something that deserves more attention.
All right. I didn't know that. Thank you for that explanation. If we move on with the same figure, there is a distinct difference in the stratification behavior between the first and the second period.
Yeah.
In the first period, the density difference between the top and the bed layer, that's the red line, maintains during low tide. Whereas in the second period, it drops after, or actually before low water and afterwards.
Yeah.
What could be the explanation for that?
We do have an explanation for that, and for answer your question, I would like to show you some. So what happened during this measurement was the stratification of the water column. This, what I'm showing here, first off, is the stratification of the 12 meters depth mooring during Strain's experiment in 2013. This work was by Alex Horner-Devine. I'm just blurring here the 18, that's not really important. And what happened that in the first period, the water column was strongly stratified. And I think, if I remember correctly, the river flow, the river discharge was twice as the historical average, was really big. And then had a lot of baroclinic processes taking place there, not only tidal straining, not only estuarine circulation, or the incidence of the fronts of the river. So then he classified himself this period as a typical rollfish training. So we don't see clearly this same diurnal switching of stratification. There are a lot of stratification and possibly another baroclinic process there. So that's why we don't, the pattern, my figure here, we don't see this switch in same diurnal switch of stratification. And the second spring here, so we see a mix between front and straining happening at the same time, right? So the front, we can see those little peaks here between high and low water, right? Just a few hours after high water, that we also see in the newer data set. So we see here those little peaks here due to front. So we also can recognize here, but it lasts much longer, right? So probably this is to the effects of straining as well. So they're combined here. So it's really interesting how to see, it depends on the stratification regime.
And the fact that the river discharge is decreasing in this period, does that play a role? Or is it secondary?
Also, it's decreased. And it's not only the discharge, we also need to take into account the winds. That's not shown here, but the winds also play a very important role on the position of the plume. And because of that, you can see different kinds of stratification, like we see here. So it's a combination of discharge and winds, I would...
Because it occurred to me in your second data set that there was only a minor difference in the wind. It was wind force 3 versus wind force 4, actually. And it had quite some implications, right?
Yeah.
So are you saying that it's very sensitive to wind fronts?
I would say
or
that.
wind-induced fronts?
Well, I think the role of the winds, there are more people look into that in more details. But the winds, I think you can think of few things, right? First, the effect of the wind, what we would call an ageostrophic wind. That's like if a wind blowing in a direction, going to have the effect on that direction. So, for example, if you have the wind blowing from north, the ageostrophic wind would sort of block the river plume, right? But if the wind persists, then you start to see some, the wind start interacting with, for example, Coriolis and other large-scale processes, and then you have like Ekman motion. So in this, we call it the geostrophic wind. Then in this case, would push the plume to offshore, and then you have sort of upwelling circulation. And also have the fronts that are even more complex, and the winds also play a role. I wouldn't be able to really detail for you how the fronts happens, but yeah, that's why you see all those differences in stratification in those periods. So it's a combination of discharge, winds.
Okay, so I understand, I accept there's a difference there, but now to your conclusion. What you concluded on the basis of this figure is that the rapid increase of stratification after high water is associated with a delay of the tidal delay of the decay of the tidal stresses, right?
Yeah.
That's the little hump in the green profile.
Yeah, yeah.
Now, in the second part of your tidal signal, there's a clear difference in stratification, but the green line behaves similarly.
Yeah, we don't see that clear.
So apparently that effect is not there if the opposite process occurs.
Maybe it's in there, but it's milder. It's something that, yeah. But yeah, I think all depends on this how stratification do play a role there. So in these three cases, but indeed, so we don't see that clearly in this. We do see a little ramp. I mean, this velocity, sorry, it's not stress, but it's much milder than when we see here.
But your conclusion that it's related to stratification, the first hump, is still valid, even though you don't see it in the second part.
Well, yeah, maybe I should explain that better, but it's related to stratification, but it depends on how the stratification it's taking place in there, right? If you have sort of a typical role for straining, or if you have like combination between straining and fronts, or maybe only the classic tidal straining, that should be more clear, I agree.
Right. Thank you. Is there time for another quick question?
Quick question, quick answer.
Okay, the second question was about the upscaling. So you carried out very detailed measurements at distinct locations in the cross-shore. And then you come up, and this builds on the questions that were asked earlier by colleagues Valkes and Roelvink. And then you come up with conclusions about the impact for future nourishments, so to say. How do you upscale these individual point measurements to a spatial pattern that you need for the design of these nourishments?
I think we need a model for that. Or unless you have a lot of money, a limited budget to have a lot of instrumentation, which I think is not the case. But a model. The point is, I tried to run a model, and it's really complicated when you include the baroclinic processes. First, you need a 3D model. And then with a lot of layers, it requires a lot of computational effort, right? Yeah. And we didn't get nice results with our model. We tried for, I don't know, maybe 2 years to have students to work on that.
Yeah, we had a little help of Marijn Hoop.
Yeah, exactly.
And he came with cross-shore sediment transport rates in the order of 2 to 5 cubic meters per meter, right?
Right, yeah.
And if you consider those absolute values I mean, of course, there's uncertainty, but if you consider those absolute values, is it still crucial then to include these density differences in the design of future nourishments?
I think so. Well, crucial is such a bold statement, right? I think the work, the Dutch coastal community does is already great and is to the age, right? However, if you really want to fine-tune your modeling, if you want better results, if you want to, for example, still know better if it's needed to keep the volume of sand up to 20-meter depth, then I think not only my research, but all the small contributions about it, it's important, because in the end you have really a better understanding. For example, the fact that the bed load goes to the south and the suspended load go to the north. And I read paper about the sediment budget here, and there are some authors that claim that the bed load is more important in the inner shelf, and there are others that claim that no, it's the suspended load. So there's still not a general agreement about it. So I think that's where my humble contribution comes in.
I think for long-term coastal behavior, those small-scale components are indeed important.
Yeah.
But if it comes to the design of the sand engine, where you lose 1 million cubic meters in 1 year, 5 cubic meters per meter over 2 or 3 kilometers, is a little less.
Well, yeah, indeed. But again, nobody expects the sand engine to roll that fast, right? It was supposed to be in 20 years.
Well, 20 million cubic meters, 1 million in the first year.
Yeah, but
not the right pace, and it slows down now a little bit.
Yeah, a lot. So there are still missing links that might be explained by certification, or we never know. So more studies are needed.
Thank you very much.
Yeah.
Thank you for the opposition. Then we go to this side of the room. I can give the floor to Professor Pietrzak, promoter.
Thank you, meneer de Rector. Waarde promovendus, I'd like to start by saying I enjoyed reading your thesis very much. And I think something you might have learned in the past few years is I like sketches.
Right.
So could you make us a sketch to show basically the Rhine-Rophy, what happens during a tidal cycle with the surface circulation and what happens at the bed, so that we can discuss the role of tidal straining on sediment dynamics versus the fronts, which you nicely put up.
Do you want the whole explanation about the...
Oh, yes, please. And how that links to your results.
So start with training, maybe? Okay. We should, let's assume that the tide can be decomposed in a cyclonic and an anticyclonic part, right? So let's say U plus, it's cyclonic, it does the tidal amplitude, and U minus the anticyclonic. If you look at for example, across shore tidal profile, and look at also the boundary layer, right? So we have the boundary layer related to the cyclonic, cyclonic, and the anticyclonic here. So if you look at the boundary layer in a well-mixed situation, right? What we see, let's call this guy here. This is the anticyclonic boundary layer, and this is the cyclonic one. This anticyclonic boundary layer feels much more the bottom drag, so that's why it's much bigger. And then if I'm corrected, the ratio between them both is about 3, right? So now in the stratified situation, what we see is now I have a pycnocline here, right? Stratification. And on the bottom, so you see this boundary layer here, and this one here. more or less having the same behavior. I would even argue that this slows down a little bit more, slightly, because all the bottom drag now is confined to the lower layer. But then, this guy now here that feels a lot of the bottom drag is free to move above the Picnock line, and then that just, oh sorry, this should be dashed. And this guy just a little bit. So now you have these. Yeah, and this. So this difference here, we can understand as the ellipticity, the circular motion. So now the tide is much more, the tide excursion is circular. So there would be the ellipticity. That's the measure we use to sort of explain tidal straining, right? So you see that in the surface, but in our case, you have also the coast here. Let's say I'm just exaggerating here. So here's the coastline. So if you have a cross-shore flow hitting the wall, the coastal boundary, so we need to be compensated, right? So you create like the opposite. And this creates the horizontal difference in stratification, and then interacts with the tidal profile, the tidal shear, and then we see the tidal straining going on, right? So over a tidal cycle now, so if here's high water, here's low water, we have stratification growing from here to here and decreasing from here to here. And here's a one tidal cycle. I don't know if it's clear for everybody, but right. And then the impact that on the sediment transport. That was your next, right? So here, what we have, it's from high to low. If you look at the cross-shore profile here, you have, I need to put some more thought. So this is a cross-shore profile. You have an onshore current on the near bottom and offshore in this, well, that grows here, and here's the other way around. So here what you see, it's onshore movement in the surface and offshore near the bed. I hope I'm right. And yeah, and then we see the impact, at least in the cross shore. Then we see that there are more onshore transport from low to high, and the other way around from high to low. This is in the cross shore. In the long shore, though, I think the baroclinic tidal flow matters, but is more responsible for, well, the barotropic also is very strong. So in the longshore, I would argue that, you know, the transport is, I mean, stratification is not that relevant if you compare with the cross-shore component. The stratification has a much more impact in the cross-shore transport than in the long-shore transport. But I don't know if I have answered everything or where we're heading to now.
I'm happy with your answer. In view of time, I think...
Okay, thank you.
Thank you.
Yeah.
Nice explanation.
Let me go to the next promoter, Professor Renius.
Waarde promovendus, beste Saulo. It's been a pleasure